Hello everyone. In the previous lecture on the Castiglione's theorem on deflections, at the very end I had mentioned that I had finished the theory part and that we will be going on to problems, but I realized that before I can actually go on to start solving problems, I'll have to lay some basic groundwork which will look a bit like theory. So that I have titled today's lecture as Prelude to Problems. Okay, so this is neither really theory but not really problems, something in between. So our intention here is to use the Castiglione's theorem of deflections, which was as written last time, to find out the deflection along the direction of a force applied at a certain point, which is represented by this UF bar. We have to use this derivative with of this U dash, which is the complementary energy. Now we had also mentioned in the previous lecture that this U dash for Hookean materials, that is for linear elastic materials, we had mentioned that this U dash is equal to U, which is the strain energy. And mostly we will be dealing with the kind of problems which are made up of these linear elastic materials, in fact linear elastic isotropic materials. So we won't be bothered too much with this distinction between U dash and U, but we will be also solving problems, at least one illustrative example involving a nonlinear material, for which we'll have to go down the route of using the U dash. But even before that, okay, even for, let's say we want to use a linear elastic material where we can use the strain energy directly U, we have to be a little bit careful in the usage. Okay, so towards that end, you first note that this U is equal to the integration of the strain energy density, which is per volume, like this. All that is fine, but what exactly is the form of the U that we should be using, especially when we are interested in solving beam problems? Okay, now some of you may already be familiar with the operational bits of it, but what I wish to highlight here is that we should not be directly jumping to any kind of formula which we may know from our undergraduate days. For example, if I asked you about the expression of the strain energy, many of you may actually jump to the so-called famous formula that this U naught is something like half sigma epsilon. Okay, so we have to be a little bit careful before carelessly writing something like that. Okay, so what I will do here is I will write down the expression for the strain energy density U naught for a linear elastic isotropic material in this fashion. Okay, so let me write this down and then we can go into a discussion of this. So here, this lambda and g are the Lamy parameters which we had discussed back in our course of applied elasticity. Here, this IE is the first invariant of strain. This Roman 2E is the second invariant of strain. I repeat, these two are the first and the second invariants of strain. There is no third invariant of strain involved here. Likewise, this can be equivalently represented in this fashion: 1 by twice E I1 square minus 2 into 1 plus nu I2, where I1 and I2 are the first and the second invariants of stress. So in the previous line, IE and this 2E were the first and the second invariants of strain. Here in this line, I1 and I2 are the first and the second invariants of stress. Of course, this capital E is the Young's modulus, this nu is the Poisson's ratio. So where do we get these expressions from? Okay, so that is a discussion which I will go into these discussions a bit later, because I do not wish to break the flow of the current discussion, where I want to go into a form of the strain energy which will be actually usable while solving problems of involving beams, okay, based on where we apply Castigliono's theorem. Okay, so I'll cover this part in this lecture itself, but first I would like to proceed with the strain energy as it is. Now, if we consider the second bit, okay, the second formula, then especially considering thin rods, okay, mostly in the case of typical loading scenarios like bending, the only stress which will be dominant, okay, is the one involving the sigma 1 1. Okay, you understand this I1, it is equal to sigma 1 1 plus sigma 2 2 plus sigma 3 3. That sigma 1 1 we are talking about. The rest of the normal stresses as well as the shear stresses which would be involved in this expression of I2, those are non-dominant. In such a scenario, okay, so for thin rods under maybe axial loading or bending, okay, let's consider bending because this will be the case for which we'll develop our formula subsequently. For thin rods under bending, it is the sigma 1 1 which is dominant. Okay, sigma 1 1 is dominant over everything else, which means that u naught, it basically reduces to 1 by twice E sigma 1 1 square, because you understand I1 is equal to sigma 1 1 plus sigma 2 2 plus sigma 3 3. If sigma 1 1 is dominant, we don't have to bother about sigma 2 2 and sigma 3 3, and this is only what remains. Similarly, this I2 would involve sigma 1 1, sigma 2 2, those kinds of products, but since for all intents and purposes sigma 2 2, sigma 3 3, they are considered 0, so also the shear stress terms, this won't contribute anything to the final result here. Okay, now for the strain energy of an entire beam, we are going to use this, and then we can directly use what we have obtained in the previous page. I'm going to write this as sigma. I can write this as sigma 1 1, or if you understand that the one direction maps with the x direction, the familiar x direction from considering a rectangular Cartesian coordinate system. So this is like that, integrated over the entire volume. Now for a beam, okay, for a beam, we know from our undergraduate studies that for this kind of a simple scenario, especially based on the Euler-Bernoulli hypothesis, and I'm not going to go into the details of that, this sigma can be expressed using the bending formula, the bending stress formula, or the more famously called flexure formula, in terms of the bending moment. Now this is a very, very important point to note here, that the bending moment, so we understand that this sigma is my by I. Okay, you will get a plus sign or a minus sign here depending on the choice of your coordinate system, but as you can see, we do have a square present here, so it really doesn't matter whether you use the minus sign or the plus sign. What is important, however, is to realize that since we'll be carrying out this integration over the entire volume, which means along the we have to integrate over the length of the beam also, in addition to its to an integration over the cross-sectional area, and there is a possibility that this bending moment will have a certain variation along the length of the beam, so we have to be a little bit careful here. So what we'll do is we'll decompose this overall integral volume in this fashion. So first integration is over the length of the beam, and we say that this lengthwise direction is the x direction, the x from the rectangular Cartesian coordinate system, and this area integration. And what we'll have here is, so I take this 2e, I can take it outside. Okay, for the time being I'm keeping it outside. This sigma is it gives us m square y square by I square. The first integration is with respect to the area, the second is with respect to this x coordinate. So this dx corresponds to the 0 to L, and this dA corresponds to this integration over the A. Now please note that this I square is a constant for the area. So if we actually consider prismatic cross sections, this can very well be taken outside this area. Okay. In fact, for prismatic cross sections, we can have this I square coming out of this integration also. But for now, we'll just keep it outside this area integration. Okay, because in general we can have non-prismatic cross sections also, and you'll do a problem like that. However, please note that we strictly cannot take this m out of this 0 to L integration. Okay, so we take the m outside also of this area integration, no problem there. So we keep it like this. This is y square dA dx. Now what this thing is, if you think about it, you'll realize that this is nothing but the second moment of area, which is just this I. Okay, so this integration over the entire area, y square dA, that represents the second moment of area. So what we have is this thing. And usually this is written as okay, and we'll see an application of this formula when we want to find out the deflections in response to point forces applied on cantilever beams, on simply supported beams, so on and so forth. There will be certain things to be careful about there also. But now, so this is the thing which I wanted to present as one of the main things in our prelude, in our basic groundwork before launching into problems. Okay, so from that sense, this is done. But let me not forget about what I had promised in the previous page, that I would be discussing a bit about these things that I have written. How do we arrive at these expressions for the strain energy density? Okay, so let's have a discussion about that. Regarding the form of the strain energy density. All right, so we have already seen earlier that sigma ij is equal to del u naught del epsilon ij. We have already seen that. Now, many of the things that we'll be discussing subsequently, okay, some of the crucial things that we'll be discussing will be based on our understanding of this formula. But first of all, you note that this u naught, okay, and I have also mentioned this earlier, this u naught is dependent on deformations. Okay, the strain energy will be dependent on deformations. Additionally, it may also be dependent on the temperature, on the heat flux, but for at least within our scope of advanced mechanics of solids, we shall not be bothered with those kinds of dependencies. So this dependence of the u naught on deformations, we will formulate that by writing the u naught to be a function of epsilon ij. So all the deformations, all the information in the deformations, we capture it within this epsilon ij. So just a brief note before I say anything else. This little discussion that I'm about to embark on, this is basically a very summarized, non-formal, non-rigorous discussion of what we usually have in a proper continuum mechanics course. I mean, the scope of advanced mechanics of solids, it certainly doesn't allow us to launch into that kind of extensive discussions. But if you are really interested in that, in those kinds of discussions, I will provide a link to a very good set of lectures in the details of this YouTube video, and you can take a look at that. Okay, for now we stay happy with this limited discussion, but I hope that even with this limited discussion, it will give you some idea with the underlying concepts. Okay, so to proceed forward, one very crucial thing to note here is that there is a little bit of an issue when we say that the strain energy density is dependent on the strains, because you see these strain components epsilon ij, as we have seen already in our course of applied elasticity, it is very much dependent. So epsilon ij, so these strain components are dependent on the choice of coordinate systems, on the choice of our coordinate system. However, our u naught, that is a physical quantity. That's a physical truth about the system under consideration. So how can this physical quantity be dependent on the choice of the coordinate system? So it must be independent of the choice of the coordinate systems. It should be that way. Okay. Now you see where the issue is. On the one hand, we are saying that u naught should be a function of this epsilon ij, and on the other hand, there is this apparent discrepancy where these strain components are something dependent on the choice of the coordinate system, but u naught, we want it to be independent of the choice of the coordinate system. Okay, so this apparent discrepancy that we have here, how can we resolve it? Okay, so there is an apparent discrepancy here. Okay, so this is something dangerous. Okay, so here it is independent, here it is dependent. So something has to be fixed here. How can you fix it? So if you think about it, there is a way out. Okay, so in one of our live sessions that I had just today, I asked the questions to the students, and very nicely, two of them had come up with the answer. That one of them said that uh, suppose we require that u naught is dependent on the principal strains, because as we know, the principal strains are independent of the choice of the coordinate system. So that's a very nice answer. And another student said that perhaps we can involve the strain invariance. So that answer regarding the strain invariance, that is the official textbook answer, and of course the other answer is also correct, that the principal strains, because we know that the principal strains are indeed influenced or dependent only on the strain invariance. In fact, back in our course of applied elasticity, we had done some problems and we had discussed this particular aspect. So going forward, what we'll say is that while our initial thought was that u naught would be a function of epsilon ij, but in reality, to fix this apparent discrepancy between the dependence and the independence of the choice of the coordinate systems, what you have to really say is that u naught is actually a function of the strain invariance. So IE, 2E, and 3E. These are the three strain invariants. Alright, so far so good. Now, imagine that we wish to capture the linear elastic behavior, which is quite common in many engineering systems. So we go back to our expression, the sigma ij is equal to del u naught and del epsilon ij, and we think about it for a while. You note that if you think a little bit carefully about it, you will see that suppose this u naught was just linearly dependent on this 3e. I repeat, suppose you imagine that this u naught has the simplest of dependencies on this 3 through some kind of a linear relationship. Maybe there is a term in this expansion of, so till now we have not written down this form of how they are connected. We have just written that they would be dependent on this, u naught would be dependent on this, but we have not written down the exact form. We don't know yet. But suppose you imagine that that u naught has the simplest of dependencies on 3. Maybe it is just multiplied by a coefficient and then 3e. Then what will be the implication of that? Implication is that this 3e, it is basically the determinant of the strain matrix. Okay, it is the determinant of the strain matrix, and each of the terms in it involves 3 of the strain components. Okay, so because this 3e, the third strain invariant, it involves as its various terms 3 of the strain components. So these are like cubic powers. So these involve cubic powers of the strain components. So if we do this kind of a first derivative of that those cubic terms, you will end up with a relationship between the sigma and the epsilon, which involves quadratic terms at best. Okay, you will never ever obtain linear terms. Okay, so remember that this is under the supposition that u naught is having a linear dependence on this 3, and if you were to think that it is more than linear, then it's even a worse scenario. Okay, so even with a, so let me go to the next page. So remember that we are considering the scenario for linear elastic behavior. For such materials, okay, if u naught just depended on 3e even linearly, then sigma ij is equal to del u naught del epsilon ij would lead to a, a dependence of sigma ij on quadratic terms of epsilon ij. Quadratic terms of epsilon ij, or rather I should write quadratic terms involving the strain components. That would be more clear. And that happens because involves cubic terms of the strain components. Okay, so our conclusion is that at least for linear elastic materials, what we had initially thought that u naught would be dependent on I1, I2 and I3, that would be wrong to assume, and what we must conclude is that the only dependence of u naught should be on IE and 2E. And please note that this is again for linear elastic materials. Okay. Please note that our conclusion is based on the simplest possible linear dependence of u naught on 3E. Okay, so if the scenario is like this, even for a linear dependence on 3, you can imagine that for higher order dependencies the scenario would be even worse. Okay, so certainly we must not depend on 3E for this u naught. Next, let us consider the IE, that is the first strain invariant. Okay, again you consider that u naught depends on IE. Okay, so suppose if u naught indeed were to depend on IE linearly, okay, this is very important. If it were to depend on IE linearly, then let's write this. Okay, so if u naught depended on IE linearly, sorry about that, then sigma ij is equal to del u naught del epsilon ij would produce a constant term. What that means is that such a constant term would represent some non-zero value. Okay, so this constant term would represent a non-zero value of stress even in the absence of deformations. You think about it, even in the absence of deformations. So suppose you have sigma ij is equal to 10 megapascals or something like that. If you get such an answer, what it means is that even if your epsilon ij is not there, then also sigma ij is equal to 10. Okay, maybe you have something like sigma ij is equal to 10 megapascal plus it has some dependencies on epsilon ij in the other terms, because we have not yet talked about the dependence on this 2e. We are only talking about how u naught is depending on this IE. the first strain invariant. If it so happens, as we are saying, that it depends linearly on this first strain invariant, then it results in a constant term, and such a constant term, it represents a non-zero value of stress even in the absence of any deformations. Deformations means in the absence of deformations means epsilon ij is 0. Now, physically speaking, there may be certain situations where such a thing is very much possible. Okay, but that's not extremely common. In the typical engineering situations that we are interested in, and especially within the scope of advanced mechanics of solids, we don't want to be bothered with such kinds of special situations. Okay, we want to have a situation where you only have stresses when there are deformations. Okay, so what we say is that all the possible physically we will not consider such situations. Okay, we will not consider such situations because it involves taking some special care on some other things. Okay, will not consider such situations. So if we do not really wish to consider such situations, then what we had started out with here, that u naught dependent on this first strain invariant linearly, that is a no-go. Okay, so we must conclude that this u naught should be having such a form that it does not depend on the third strain invariant, it does not depend linearly on the first strain invariant. That is the conclusion. Okay, so u naught should not depend on IE linearly. This is very important to note. Please do not conclude that it should not depend on IE. Okay, because you see, the thing had gone really bad when we had taken even the linear dependence on 3. But here we are saying that if we take the linear dependence on 3, then it is bad, but it is very much possible that u naught can depend quadratically on this IE, and then we will be good, because then it would not lead to this constant term. Okay, and in fact this is what we are going to say in the next page. So overall what we can say is that if so u naught should depend on terms. So this is the moral of the story that we had been talking about in the previous page, that u naught should depend on terms that are quadratic in the strain components. Okay, and such a thing can be ensured. Okay, such a thing can be ensured if our u naught depends on IE square and directly on the linearly on the okay. So when I say it depends on IE square and 2e, I mean to say that it depends directly or linearly on this IE square and 2e. So basically what I'm saying here is that u naught should have the form some constant term multiplied by IE square plus some constant term times 2e. And now if you take this thing and you utilize this if you carry out this thing, okay, substituting appropriately the index notation expressions for this I square and this 2e and proceed. It will involve some steps. So if you proceed with that, ultimately you will arrive at a relation between sigma ij and these epsilon ij, which are all linear. Okay, so ultimately if you proceed, ultimately you will end up with sigma ij linearly dependent on epsilon ij components. Now overall in this story, I have actually hidden from you one little aspect, that in our arguments here, I mean the way that we have proceeded, it is actually not just linear elastic that we would be arriving at here, this final expression. Rather it will be the linear elastic isotropic. Okay, but the arguments involving the isotropic thing would entail a little bit more discussion, so I'm not going into it, but I'm just telling you, and you please accept it on good faith, that what the kind of steps that we are proceeding with here, that would ultimately lead to an expression of the sigma ij that is not just linear in epsilon ij, but it will be of the form that will also be isotropic. I mean, you don't have to accept it in good faith, in the sense that you can actually do this thing and you can see that yes, it is indeed isotropic. But what I'm really hiding from you is that when I'm arguing for the case that u0 depends on this I square and 2e, there I'm specializing to the case of, in that argument itself, I'm specializing to the case of isotropy. Okay, so for non-isotropic behavior, for an isotropic behavior, you'll have a little bit more general expressions. Okay, so let's not get into all of those things. And interestingly, if you actually compare, okay, so whatever expression you get, if you compare that, you compare the above with the familiar expression of linear elastic isotropic behavior, which we had discussed extensively in our earlier course of applied elasticity, that lambda epsilon kk delta ij plus twice g epsilon ij, you will end up with the kind of expression which we had discussed back here. Okay, so this expression which we had discussed back here, you will end up with that. All right, so with this little prelude, okay, but deep, I mean little but deep prelude, I think we are all set to tackle problems, and we'll go on to problems. Okay, thank you very much. I'll end the video here.